Hello everyone, my name is Rajeev and I'm a chemistry master teacher at Vedantu. Today I will be talking about angular wave functions and their role in the shape of orbitals. Although my primary focus would be the angular wave function, but I will briefly discuss the radial wave function also, and then I will move on to the main part, that is the angular wave function, where I will tell you how to identify a given orbital if its angular wave function is known, and then using the angular wave function can we justify the shapes of the orbitals which we already know, like S has spherical shape, P has a dumbbell shape. All those shapes can be justified from the help, with the help of the angular wave function. Now to begin with, let us first discuss the spherical polar coordinate system. In the Cartesian system, when we have any point in 3D, the coordinates of that point are x, y, z, where x represents the distance on the x-axis, movement x-axis, and y represent the distance on the y-axis, and z represent the distance on the z-axis. The same point can also be represented in the polar system. In the polar system, the coordinates of that point would be r, theta, and phi, where r represents the distance, shortest distance of that point from the origin, and theta is representing the angle of the line joining the point and the origin with the z-axis, and phi is representing the angle between the projection of that line on the xy plane from the x-axis. So r is the shortest distance from the origin, theta is the angle of the line with the z-axis, and phi is the angle of the projection with the x-axis. Now the interconversion of the polar system to the Cartesian is important because I will be using that in today's session also. So how do I convert these into Cartesian coordinates? To convert them into Cartesian coordinates, we'll have to find the x, y, and z value corresponding to this r, theta, phi. So to find the z value, we can simply drop a perpendicular from the point on the z-axis. So this distance is r cos theta, which is nothing but our z coordinate of that point. So z is equal to r cos theta. If you take the projection of that line on the xy plane, the length of that projection would be r sin theta. And to get the y and x coordinate, let us drop the perpendicular from this point on the y-axis and z-axis, x-axis. So from this, we get y as r sin theta sin phi, and x as r sin theta cos phi. Okay, x is r sin theta cos phi, y is r sin theta sin phi, and z is equal to r cos theta. Now coming to the wave function, this is the wave function in the polar coordinate system, which has three variables r, theta, and phi. We can also write the wave function in terms of Cartesian system, that is x, y, z, but we prefer to solve the Schrodinger equation in polar coordinate system because it lets us solve the three variables separately and then multiply them to get the complete wave function. Meaning, when we write the Schrodinger equation in r, theta, phi, we will be able to separate one term containing only the r variable, one term containing the only theta variable, and one only containing the phi variable. And then we will solve them separately and multiply them in the end to get the complete wave function. The first part of the wave function is known as the radial wave function. Radial part. And this part is known as angular wave function, which is the main topic of today's session, the angular wave function. The angular wave function I can further write as a multiple of p theta, which only contains theta as a variable, and f phi, which only contains the phi as a variable. This only contains the r variable. Notice there are three quantum numbers: principal quantum number, azimuthal quantum number, and the magnetic quantum number. In the radial part of the wave function, you will be able to figure out the two quantum numbers, that is n and l, which means that from the radial part of the wave function, I will be able to tell which subshell that is. Because if n is known, L is known, I will know whether it is a 3p subshell or a 2s subshell or a 4d subshell, whatever, I will be able to find that. But I won't be able to tell the orbital of that subshell because there is no ML term in this. So to get the orbital of to get the orbital also, you need the angular part of the wave function, which has L and ML as the quantum numbers. Okay, so we will see that some examples of radial wave function, and then we'll talk about the angular wave function. But before that, Born interpretation of the wave function. Max Born said that the psi values can be real, they can be imaginary, it can be negative, it can be positive. So it doesn't have any physical significance. But the psi square represents the probability of finding the electron at one point, at a point in a small section in the space. So the psi square, which is known as the probability density, is proportional to the probability at a given space. The psi square is also written as a multiple of psi and its conjugate psi star, in case if it is imaginary. If it is real, then both would be same, it won't make any difference. He also suggested that the probability of the electron you can calculate by multiplying, this is the probability density, so the actual probability of electron in the space in any region, if you want to find, it will be integral multiple of psi square into d tau. Now this d tau is basically in 1D system it will be dx, in 2D system it will be dx dy, and in 3D system it will be dv, that is dx into dy into dz. All right, so you can integrate that for a given range you're interested in from A to B, and this will be the probability of finding the electron in that region. Now remember, the probability cannot exceed 1. So sometimes when you have a wave function, and so you have to normalize that wave function. Normalization means that you have to multiply the wave function with a constant, making sure the total probability from in the entire space from minus infinity to plus infinity should not exceed 1. So that is known as normalization of the wave function. So a normalized wave function is the one in which the total integral is equal to 1. So if your wave function is not normalized, we can normalize it using this relation. Let's take one example on normalization. Assume that a wave function for a system exists and it's and it is psi. It is only in one dimension. Only one variable is that is x. So psi x is equal to sine pi x by 2, where x is the only variable. If the region of interest is from x is equal to 0 to x is equal to 1, meaning the system, the electron doesn't exist, or whatever the particle is, doesn't exist before x is equal to 0 and after x is equal to 1. This is the only range in which it can exist. So we have to normalize this function. So it means that in this range, the probability cannot exceed 1. It has to be 1. So to normalize the function, I will use that from 0 to 1 psi square into dx should be equal to 1. Right? For that, I will have to multiply this with a constant n, meaning let us assume that the normalized wave function is n into sine pi x by 2, so it would be n square psi. The normalized wave function should have the overall probability to be 1. Let us put the values. So n square 0 to 1, this would be sine square pi x by 2 dx should be equal to 1. Solving this, n square, this integral will be x by 2 minus 1 upon 4 times pi by 2 sine 2 pi x by 2. limits from 0 to 1. So this would be, and this should be equal to 1. This should be n square x by 2 minus 1 upon 2 pi sine pi x. 0 to 1 should be equal to 1. This implies n square, putting the values of putting the limits, it is 1 upon 2 minus sine pi would be 0, so this is 0, and when you put the lower limit, then this is 0 and sine 0 is again 0. So this is equal to n square should be equal to 2. This implies n should be root 2. So your normalized wave function for this system would be the normalized wave function would be root 2 sine pi x by 2. Now this will satisfy the condition that the overall integral in the space would be equal to 1. Let us take some examples of normalized radial wave function. These all are normalized radial wave functions. As we know that in the radial wave function, the two quantum numbers we use, we get a n comma l, right? So this R10 means this is n is equal to 1, l is equal to 0. So this must be representing a oneness subshell. This 2, 1, this must be representing one of the orbitals of 2p subshell. This is 2s, this is 3d, this is 3p, and this is 3s orbital. Now if you notice that in all these radial wave function, you will find some similarities, and using those similarities I will be able to generalize the radial part of the wave function, because I don't have to memorize these wave functions. I simply have to know the general form of the radial wave function, and if the wave function is given, I should be able to identify that it is representing which subshell. Basically, I should be able to calculate the n value and the l value from the given radial wave function. Okay, so if you notice, in all of them there is a common term, e power minus zr by a naught. So in the general form of radial wave function, there will be a term e power minus zr by na naught. Here it is 1 a naught, here it is 2 a naught, here it is 2 a naught, 3 a naught, 3 a naught, because the n value is 1, 2, 2, 3, 3, 3, that is fine. So whenever you get any radial wave function, the exponential part of that will directly give you the n quantum number, that is the principal quantum number. Now L is remaining. How to get the L value from the given radial wave function? You notice that there is a constant term in all of these radial wave function. The constants are different, but there is a constant term because Z is atomic number, a constant value. A naught is Bohr radius, a constant value. So every wave function is multiplied with a constant K. Apart from that, there are, like here you notice, this is a quadratic equation. This is a quadratic equation. This is a linear equation. This is a linear equation here also. So there is also a polynomial in R. But notice that the polynomial will always have a constant term here, like zr by 2a naught, then there is a constant 1. Zr by 6a naught, there is a constant 1. Zr square, zr by, then there is a constant 1. Meaning I cannot take this as a polynomial in this case, because this does not have a constant term. I cannot take this as a linear polymer in this case because it does not have a constant term. Okay, these values which I am just highlighting, they don't contain a constant term. They are simply present as a power of R. So there is another term present in the wave function, radial wave function, that is R raised to the power L. and from there I will get the L value. I've already got the N value, I need the L value. I will get the L value from these parts. Okay, so apart from the polynomial, because it is very easy to distinguish them, that this is not a linear polymer, this is the R power L term, because if it were a polynomial there would be a constant term in that along with the ZR by A naught. So it is not that. This is a linear polymer, right? This is quadratic, this is linear. So this R power L, like here the R power is 1, so it must be representing P subshell. Here R power 2, it must be representing a D subshell. In case of S, you don't see that term of R power L, because in this case I can write it is R raised to the power 0. In 1S or in 2S I can write this R power 0. Here also I can write this R power 0. So apart from the polynomial, the R power L term will give you the L value, and you will get the N value from the exponential term, and that way you will be able to figure out which subshell this radial wave function is representing. There is one more point which we can use, that the degree of this polynomial is n minus L minus 1, n minus L minus 1, where n represents the principal quantum number, L represents the azimuthal quantum number. This is basically the number of radial nodes. You must be knowing this already, number of radial nodes. It simply tells us at how many values of R this polynomial becomes 0, apart from R is equal to 0 and R is equal to infinity, because at R is equal to infinity, because of this exponential term, this function becomes 0, and at R is equal to 0, because of R power L, this becomes 0, except in S subshell, because in S subshell this is R power 0, which means it is 1. So all the radial wave functions except the S orbitals would be 0 at R is equal to 0 and 0 at R is equal to infinity. So this will be a common point if I plot R and distance graph. So they will be 0 at R is equal to 0 and 0 at R is equal to infinity. In between these values, how many times it will be 0 will be given by the degree of this polynomial, the number of solutions of that polynomial. Alright, if it's S subshell, then at R is equal to 0, it won't be 0, it will start with a positive value, and it will be 0 at R is equal to infinity because of exponential term. So suppose you have this R21. Let us plot the graph for R21. So I know that in this case the polynomial is having degree 0. N is equal to 2, L is equal to 1, so 2 minus 1 is 0. So it won't be 0 at any point except origin and infinity. At origin it will be 0 because there is R power 1, so R is there. When you multiply this with R, it becomes 0, and infinity it will be 0. So it will look like this. This is the radial wave function for a 2p orbital. For let's say a 3p orbital, in a 3p orbital the polynomial has degree 1. It's linear polymer. It has one solution. At one value of R, this function would be 0. So apart from R is equal to 0 and R is equal to infinity, it will also be 0 at some other value of R, which is the solution of this polynomial. So at R is equal to 6a0 by z, this value will be 0. So the graph will look like this. Now if you take any of the S orbitals, for S orbitals the starting point would be some positive value, because none of the S orbitals would be 0 at R is equal to 0, because they are being multiplied with R power 0, which is 1. So all of them, let's say 3s will be starting with a positive value, and it will be 0 at R is equal to infinity because of the exponential term. In between the 2 points it will be 0 at 2 other values, because it's a quadratic equation. It will have 2 solutions. So it will be like this. There are 2 radial nodes in the 3s orbital. Alright, so this was the radial wave function. Let's take one example. Suppose the radial part of wave function is given as z by a naught 3 power 3 by 2 e power rho n by 2, 1 upon 32 root 15, 20 minus 10 rho n plus rho n square into rho n, where rho n is 2zr by 4a naught. If you plug in this value in the exponential, because I know that this radial wave function should be in the format of k constant polynomial r power l and e power minus zr by na naught, right? So I'll plug in this value of rho in this exponential, so the exponential term becomes minus zr by 4a naught, which immediately gives me the n value. So this is an orbital of fourth shell. Now, to get the L value, now this is this and this multiplied together would be the constant term k. Then there is a quadratic equation in the R. This is quadratic. And I also have the R part, because if you put the rho value here, it will be 2zr by 4a naught, which is zr by 2a naught. So this is basically R power 1. From this, I will get the L value. So L value is 1, N is 4. So this must be representing a 4p orbital. I can also get the L value using this number of solutions of the quadratic. It's quadratic, so the degree of this polynomial would be 2. So n minus L minus 1 is 2. N is 4, we have figured it already. So this is 4 minus L minus 1 is equal to 2. So L would be 3 from this. Sorry, 1 from this. 4 minus 1, 3. So it's a p orbital of fourth shell. So this is what we are expected to solve in the examinations also. They will give us the radial wave function, and they will expect us to they will expect us to know which is this subshell. We can only find the subshell, we cannot find the orbital to which this subshell belongs to. We cannot find the orbital of this wave function because we don't know the angular part yet. So let us talk about the angular wave function now. The angular wave function, as I told you, is a multiple of two distinct functions. One is p theta and one is f phi, and the multiple of these two will give us the angular wave function y l m for S subshell, L would be 0 and ML will have only one value, that is one orbital only, that is which corresponds to ML is equal to 0. Both P theta and F phi are independent of theta and phi, means it's a constant value. So the multiple of these will give us the angular wave function for any S orbital. It will be 1 upon root 4 pi. Now this is a constant value for any S orbital because they are not depending on theta or phi, and the angular part does not depend upon the R value. R would change the radial wave function. So this means that every S subshell will have this as the angular wave function. In P subshell there are 3 ML values, ML0, one of the orbital corresponds to ML0, one with ML1 and 1 ML minus 1. For ML0, the P theta part is root 6 by 2 cos theta and the F phi part is 1 upon root 2 pi. Multiplying them will give us the angular wave function, that would be under root of 6 upon 2 root 2 pi cos theta, and this would be under root of 3 upon 4 pi cos theta. Notice it is independent of phi, right? For ML is equal to 0, the angular part of the wave function is independent of phi, and this is going to be common in all of the orbit, all of the subshells, meaning in the D subshell we know one of the ML value would be 0, and for that the angular wave function would be only depending on theta. For F subshell also one of the ML would be 0, and there also it will be only depending on theta. So that you can just, this is a hint that whenever the angular wave function is not containing phi part, it must be representing that orbital which corresponds to ML is equal to 0. And when the angular wave function does not have theta and phi both the parts, it must be representing the S orbital. Alright. So this is representing one of the D orbitals. I don't know which one is this yet, but this is representing one of the P orbitals. The other two P orbitals will be represented by +1 and -1. Let us see their angular wave function. So for ML is equal to +1, the P theta part is √3/2 sin theta. The F phi part is 1 upon √2 pi e power I phi. Now notice that this is a complex. This contains a complex part. If you open this, this becomes 1 upon √2 pi cos phi plus I sin phi, and this would be 1 upon √2 pi cos phi minus I sin phi. I sin phi. Alright. In fact, the F phi part can be represented by a common general formula that F phi for any orbital will be given by 1 upon √2 pi e power I ml phi. 1 upon √2 pi e power I ml phi. So for all those, that is why you notice why the angular wave function is independent of phi for all those orbitals which have 0 ml, because when you put ml as 0 in this would be 1 and it will be independent of phi. Those orbitals which have a non-zero ml value, whether it is +1 -1 +2 -2 +3 -3 whatever, they will contain the phi term. So for +1 -1 there is plus I phi, and for minus it is minus I phi, and these are the F phi part of m+1 and m-1. The problem is if you multiply them you will get a complex part. You will get the y part, but that will be complex. It contains I, as you can see. We want to deal in real parts. So how do we convert them into a real part, which into a wave function which does not contain an imaginary part? So we find out another phi function, F phi function, by the combination of ml+1 and ml-1. So one of the wave function that we get is by this transformation, phi +1 plus phi -1 into 1 upon √2, and the other one we get by this transformation, phi +1 minus phi -1 into minus I by √2. When you apply these two transformations, you will be able to cancel out this I part, and you will get the phi part of two orbitals which is having only the real part. Let us apply these. So the phi part of the wave function would be 1 upon √2 pi. When you add them, then the I sin phi will get cancelled. This will be 2 cos phi into 1 upon √2. So that would be cos phi upon root pi, and similarly here the phi would be 1 upon √2 pi. When we subtract them, then cos phi gets cancelled. We get 2 I sin phi into minus I by √2. I square is -1, there is -1 already, so it becomes sin phi upon root pi. So the remaining two p orbitals will be expressed in terms of these phi. We will not be using these phi, because if you use these phi we will get a complex term. So to get the real term only, one of if I write the y part of these two, so the actual angular wave function for one of the p orbitals would be, let us write it. So for one of the p orbitals, y theta phi would be multiple of p theta and this phi part, that is root 3 by 2 sine theta into sine phi upon root pi. This will be root 3 by 4 pi sine theta sine phi, and the other one would be, this is y, sorry, theta phi would be root 3 by 2 sine theta cos phi upon root pi, which gives us root of 3 by 4 pi sine theta cos phi. Okay, I have not assigned the nomenclature to them, whether it is px, py or pz. I have got three wave functions, three angular wave function for the three p orbitals. For first of p orbital, this is the angular wave function. For other, this is the wave function, and for third one, this is the wave function. Okay, I will tell you how to identify. That is the main part. That from the given wave function, can I identify the orbital? Okay. Before I discuss that, let us talk about the wave functions for the d orbitals also. In the d orbitals, we will have 5 values of ml, 0, plus 1, minus 1, and plus 2, minus 2. Again, because it is ml 0, so the phi part will be independent of f5 part will be independent of phi. This will be a constant 1 upon root 2 pi. So if you multiply them, we will get the total angular wave function of this d orbital. It will be root 10 by 4 into 2 pi 3 cos square theta minus 1. This is the angular wave function for one of the d orbitals. One more time, for the remaining 4 d orbitals, there will be this complex part. So we will have to find the real part using those two transformations. So for plus 1, minus 1, I will be using those one time adding them, one time subtracting them, and we will get the real part, and then multiply with the p theta. The total wave function we will get as root 15 by 2 sine theta cos theta is the p theta part, and the p phi part would be cos phi upon root pi for one, and for the other one it would be sine phi upon root pi. So these are the angular wave functions of the 3d orbitals. First one this, second one this, third one this. Please notice that we are not able to calculate the angular wave function for non-zero ml values using one of the ml. We are using the combination of both the ml to get the angular wave function. For plus minus 2 also I will have to use this combination, because it will be cos 2 phi plus I sin 2 phi and cos 2 phi minus I sin 2 phi. One more time, it will be root 15 by 4 sine square theta. When you add them, we will get cos 2 phi upon root pi, and when you subtract them, we get sine 2 phi upon root pi. All right. So now that we have assigned the angular wave functions to 5d orbitals, 3p orbitals, and the s orbital. In the case of s orbital, it is very easy to identify that if angular wave function is independent of theta and phi, it will be the angular wave function representing s orbital. This will always be independent of both theta and phi. Will always be independent of both theta and phi. So that is easy to identify. Now coming to the 3p orbitals of p subshell, the angular wave function of first p orbital is root 3 by 4 pi cos theta, and for other two it is this. To convert them in the known form like px, py, pz, I will have to use that conversion of the spherical system into Cartesian system. Just let me write that one more time. X was r sine theta cos phi, y was r sine theta sine phi, and z was r cos theta, r cos theta. Now please remember from the radial wave function, let me just go back and show you this, that for any p orbital, the radial wave function will be multiplied with r power 1. For any d orbital, it will be multiplied with r square. For any f, it will be multiplied with r cube. And for any s, it will be multiplied with r power 0. Because that will be cancelled, that I will be using in the angular wave part. So remember, every p will be multiplied with r, every d will be multiplied with r square. Now, the cos theta term can be replaced with the help of z is equal to r cos theta. So from this, I can write this as root of 3 by 4 pi cos theta can be written as z by r. Now because the p orbital, there will be in the complete wave function, there will be r term. So that r will be cancelled with this r. So you're left with only one variable, that is z, which means this is representing the pz orbit. Simple. Let me repeat it one more time. We are replacing the cos theta, sine phi with the in terms of x, y, z. What we have learned in the beginning, how to interconvert them. So from this relation, I can replace cos theta with z upon r, and this r will get cancelled because it's a p orbital. So when you multiply this angular wave function with the radial wave function, r will be cancelled out. So you will be left with only one variable, that is z. So this must be representing a pz orbital, right? Here we have sine theta, sine phi, sine theta, cos phi. Now sine theta, sine phi can be written as, in place of sine theta, sine phi, I can write y upon r, and in place of sine theta, cos phi, I can write x upon r, right? So this sine theta, sine phi, I can replace this with y, so this would be root of 3 upon 4 pi into y upon r. One more time, this is a p orbital, r will be cancelled, so we are only left with one variable y, so this must be representing a py orbital. And here we have sine theta cos phi, we'll be able to replace this with x upon r, so we have root 3 upon 4 pi x upon r, and r will be cancelled. We have only one variable, that is x, so this must be representing a px orbital. So we have just assigned from the given angular wave function, I've just assigned that which one is representing pz orbital, which one is representing px orbital, and which one is representing py orbital. Okay, let us use the same method for d orbitals. This only contains cos theta. When there is no phi term, which means x and y are not, because phi relates with x and y. Phi is the angle of the projection with the x-axis, and then 90 minus phi with the y-axis. If there is no phi term, as we have seen in the previous also, if there is no phi term, there cannot be any x or y, because phi only comes in x and y. There is no phi in the z. So this must be representing z. Now whether it is z, why it is called z square? Because there is cos square theta, right? So r into cos theta is equal to z. So in place of cos theta, I can write z by r. So it will be z square by r square. And remember, r square will be cancelled because this is a d orbital, and d orbitals are multiplied with r power l, that is r power 2. So every d orbital will be multiplied with r square. So this r square will be cancelled. So we have z square term, which means it must be representing dz square. dz square. Now these two d orbitals we have obtained by combination of +1 and -1. So let us see which one is representing which of the remaining 4 d orbitals. So the term we want to replace are these sine theta, cos phi in terms of x, y, z. So I know that sine theta into cos phi can be written as sine theta into cos phi. I can write as x upon r, right? R sine theta cos phi is equal to x. So in place of sine theta cos phi, I will write x upon r, and in place of cos theta, I will write z upon r. So this would be x upon r into z upon r. Again, it's a d orbital, r square will be cancelled. So we have xz, which means this must be representing dxz orbital. This must be representing dxz orbital, right? Next one, again sine theta into sine phi can be replaced with y upon r. So this multiple of sine theta and sine phi I can replace with y upon r, and cos theta one more time with z upon r. R square will be cancelled. So this is representing dyz orbital, right? Simple. So out of the 5 orbitals, we have just assigned names to the 3d orbitals, dz square, dxz and dyz. 2 are remaining. Let us see what are those names. So this is sine square theta into cos 2 phi. Now remember, in the conversion of the polar to the Cartesian, we don't have a 2 phi term. We have cos phi, sine theta, cos theta. But we don't have cos 2 phi or sine 2 phi. So we'll have to use trigonometry to replace cos 2 phi with its formula, it's cos square phi minus sine square phi. So let me add it here. To sine square theta into cos 2 phi can be written as cos square phi minus sine square phi. So this becomes sine theta cos phi square minus sine theta sine phi square. Sine theta cos phi can be replaced with x upon r. Sine theta sine phi can be replaced with y upon r. One more time, r square will be cancelled out, so you are left with x square minus y square. So this is representing d x square minus y square. The last one, we have sine 2 phi. So sine square theta, sine 2 phi would be 2 sine phi and cos phi. We can write sine square theta as sine theta into sine phi, then sine theta into cos phi. In place of sine theta sine phi, I will be able to write y upon r, and here I will be able to write x upon r square will be cancelled, so you have a multiple of x and y, so this must be representing dxy. I hope you've understood this. How do we identify a given orbital from its angular wave function? Let's recap. So for S, it is always independent of both theta and phi. For ML is equal to 0, you will only have cos theta term, that will always correspond to pz, and here also if you notice, this only contains theta, so it corresponds to dz square. For the remaining 2 p orbitals and remaining 4 d orbitals, we have to use the combination of +1 - 1 +2 - 2, and when we do that, we get these angular wave functions, and then we replace these sine theta sine phi in terms of x, y, z, which we know from the conversion of polar system to Cartesian system. So we get one variable or whatever, then this gives me the name of that orbital, like this is a py orbital, this is the px orbital, this is a dxz orbital, this is a dyz orbital, this is dx square minus y square, and this is dxy orbital, right? Right. Let us now see the role of these in the shape of the in the shape of the orbitals. Because we know that the radial part of the wave function is independent of theta and phi. It will always be spherical, because if you're moving from origin to a point at r distance from the nucleus, you are allowed to go in any direction as theta and phi. There is no restriction. So the radial part will always give you a spherical shape. The actual direction comes from the angular part of the wave function. Now, because in s orbital, the angular part is also independent of theta and phi, so overall shape remains symmetrical only. It does not get any direction. So only s orbital will be symmetrically because even the angular part of s orbital is independent of theta and phi. Radial part of every orbital is independent of theta and phi, but for s, even the angular part is also independent. So the shape will remain spherical. There will not be any restriction on x direction. For d orbital, if we start with the pz orbital, let's say, you know that there is going to be restriction because it is dependent on theta and phi. Pz only depends on theta. For pz orbital, this angular wave function, the theta represents the angle of the line from the z-axis, right? I know that if this is the z-axis, for example, and this is the x-axis or y-axis, this is the x-axis. So for the xy plane, for any point on the xy plane, the theta will be 90. And when theta is 90, then cos 90 becomes 0, so yz would be 0. Meaning there is no possibility of existing this pz orbital on the xy plane. The maximum value of this pz orbital will be along the z-axis, because there theta would be 0. When theta is 0, then cos 0 is 1, it will have a maximum value. When you start increasing theta from 0 to, let's say, 1 degree, 2 degree, like that, then the cos theta will start decreasing from 0 to when theta is increased from 0 to pi by 2, the cos theta will decrease from 1 to 0, and this will be a graph like this. If you keep going from beyond this pi by 2 to pi, it will be again like this. This will be positive in the first quadrant, it will be negative, and then again if you increase the theta to 3 pi by 2, it will be negative, and then to 2 pi it will be positive, right? So it turns out to be a circular shape. This is a circular shape, this is also circular shape. So for a pz orbital, the angular wave function is having two circular shapes along the z-axis, above the xy plane, one above the below the xy plane. But this is 2D. Now, if you consider the phi part also, because there is no restriction on the phi, so you are able to rotate this by any angle in the space by complete 2 pi. So you will get basically make a solid dumbbell shape in positive z-axis and solid dumbbell in the negative z-axis. But when you this would be this is the shape for the y part, but the probability as per Bond interpretation is represented by the psi square. So when you square this becomes elongated and we get the actual shape that we see in the books for the PZ. This is elongated, and there will not be any sign, because when you square it, then the plus minus both become positive in y. This is y square for PZ. Along the z-axis. Alright, so this is the contribution of the angular wave function in the shape of the PZ orbital. Let us talk about this px also. In case of px orbital, the angular wave function is sine theta into cos phi. As soon as you see the sine theta term, which means that if it is theta is 0, then this value would be 0. So along the z-axis it will be 0, because along the z-axis theta would be 0 and sine 0 is 0. To maximize this value, theta has to be 90. So you have to come down on the xy plane. When you're on the xy plane, then theta is 90, so the value would be maximum. So if you're on the xy plane, this is the z-axis, this is the y-axis, and this is the x-axis. We are on the xy plane to maximize this value, because theta is maximum, theta is 90 in xy plane, and then sin pi by 2 would be 1. Now comes the cos phi factor. In case of cos phi, phi is the angle from the x-axis. So to maximize that, it should be along the x-axis. Along the x-axis. When you go on the y-axis, even in the xy plane, it is not like symmetrically circular. It is along the axis, because for along the y-axis, the phi would be 90 and cos 90 is 0. So we will have circular shapes along the x-axis, just like PZ. This is the y for px orbital. Okay. Again, when you square it, it becomes a dumbbell shape, and similarly for py, it also contains sin theta term. So you will have to the maximum probability will be on the xy plane, and there also, because there's sin phi term, so phi should be 90, so along the y-axis. Like this is the y for py. So as you can see that the actual direction or actual shape of any orbital is can be very easily understood from these theta, right? They give the direction to the wave function, because the radial wave function is always going to be spherically symmetrical. Okay, so this is what I wanted to talk about in this session. I hope you've understood it, how to find the orbital from a given angular wave function, and then using those angular wave function, how to justify the shape of the orbital. Now before I end the session, I want to give you some very important information, and then at the end I will give you a teaser question to solve and send the solution. So Vedantu has this very unique program called Eklavya batch. Every year we take admission in this batch based on the tests that we conduct. Like this year also, we in 2022 we have running Eklavya batch. For further admission in 2022, there will be another round of admissions after the JEE Main first attempt. So if you do not know about Eklavya, you can Google it and find it yourself, that what Eklavya is actually and how it can impact your preparation once you're complete your syllabus. Then at the in the last 4 or 5 months, how Eklavya can make a huge difference in the preparation. So check it out and you will find how useful Eklavya can be. I'm sharing some links which you can save, and you can keep updated. You can just you can just download these links and keep checking these this notice board. The link is also in the description. All the information about Eklavya batches, all the information about these batches will be updated there, so you can always get information from there. There you will find separate links for different batches. Like you will find one link for the JEE Aspirants 2022. Now for you guys, right now we have one Eklavya batch running, but right now the admissions are closed. But like I said, after the JEE main first attempt, there will be again a series of tests to get admission in that batch. So join this Telegram channel, and all the updates, when the test will be, all the information will be given through that channel. It's very important that you download it. You can scan, or you can download. You can also log in through this link. Then for the next year, for the aspirants of 2023, when this batch will be started, what other information we want to give you, everything will be given in these channels only. So please join the channel as per your requirement. We also have VImpact channel, the YouTube channel, where we are basically creating, uploading the past year question papers of JEE Advanced, KVPY and all. All right. So do join this channel also. Now, this is a teaser question which you have to solve and send the solution to eklavyasupport@vedantu.com with the subject line teaser solution and subject name. This is chemistry, so please write chemistry here. In the subject line, please write the subject name, and this should be the subject line, otherwise it will not be considered. We will check your solution, and if we find it like you've applied some unique concept, or if it is correct, you may get a chance to study in the Eklavya batch. Okay, that's it guys. I'll see you in the next session. Take care. Bye bye.